Hi, my name is Vahan Davudyan. I'm a physics experimentalist for 30 years. And first of all, I'd like to thank YouTube for this wonderful opportunity so we can upload our videos. Some people can upload their videos, so you don't have to be scientists. Anyone can upload their videos on YouTube, and in fact, it's like a huge network or university. We learn a lot. I have seen so many good, YouTube videos, which is so good, and people learn a lot. I appreciate that. And also, I like to thanking so many people. They emailed me, they loved my theories, and then they were asking for more and more. And in fact, every month I do, but now this has been almost 3 months. We were so busy, we had some family problems, and then now everything is taken care of, and I'm hoping every month I can publish one. And today is so important. This is one of those concepts, so many people, so many years, they were just baffling to find out what the nature of superconductivity is. Well, of course, it started in 1911, but I will give you the history exactly what happened. And, so far, I have done 46 theories I uploaded, and most of the time I have replicated many scientists' experiments as much as I could if I had the material. But overall, I had speeches in CU Boulder University, DeVry University so many times, and then Regis University, and it was so rewarding, and then so many physics students, we gave them some photocopies, and even, I helped them to do some project. Anyway, today is superconductivity, and it is one of the important concepts in physics. So the theory of superconductivity by Vahan Davudyan, physics experimentalist, and this is my email, vahandavudyan@aol.com. This started with a Dutch physicist. His name was Hayk Kamerlingh Onnes. In 1911, he was studying the properties of the matter in the low temperature. Then he was the only one. He liquefied helium, and that was great discovery. And he also got the Nobel Prize on that. And then he realized when mercury drops to 4.2 Kelvin, which is minus 269 Celsius, there was first observed that there was no electrical resistance. That was amazing. This was breakthrough in science. So in other words, what he did, he just completely stopped the kinetic energy of that mercury. Then the electricity could flow indefinitely for a long time. This is another poster. I'll put this on, you can see. Says superconductivity is a property of certain material to conduct DC without energy loss when they are cooled below a critical temperature. These materials are also expel magnetic field as they transmit to the superconductivity state. Well, of course, there were so many people worked on this, and one important one was Meissner effect, and the other one, which was, he got Nobel Prize also, Leon Cooper pair electrons, and then they also, came up with BiBCO, which is the type 2 conductor, and they got also Nobel Prize for this. So this was in Dr. Johannes Georg, and then Dr. Carl Alexander in IBM Zurich. So they got Nobel Prize for this. But what Meissner is, first of all, I have to explain, and then I have some, experiment I will show you, will clarify everything for you, because this superconductivity is a little bit difficult, unfortunately. But, I will simplify everything for you guys. So Meissner effect means, whenever anything goes with a, like a liquid nitrogen is expelling the, magnetic force. And Leon Cooper was another one which helped a lot. And then they came up with the idea that, electrons practically have the same charge, they repel each other. But, he came with the idea that, when the energy is so low, so they can get together and help and then conduct electricity in superconductivity. This happened in the state I used to live in, Denver, Colorado, and he was an amazing scientist. I attended his, lectures so many times. His name was Eric Cornell, and he was a great physicist. And he used to work with also Dr. Carl Wyman. So the Nobel Prize, it was called Bose-Einstein-Condensate, goes to physicists in 2001, awarded to jointly Eric Cornell, Wolfgang Ketterle, and Carl Wyman. This is the new state. If you remember, we had like 3 states many years ago, and then, plasma was the 4th state of the matter, and this became the 5th state of the matter, which was beyond my imagination. How could they go that low? Nanokelvin. It was almost close to the absolute zero, but no human being has ever gone this far. So what Mr. Hornell did, they got rubidium, but I have no idea how they did it. So and they had to, with laser beam and evaporative cooling, they get to this, which was almost close to the absolute zero. This was amazing how they did it. It was nanokelvin. I will show you in a minute. So nowadays we have computers, and now they can exactly show you what do we mean by atom. And then if you remember in my last theory, I was talking about the electronic microscope, scanning tunneling microscope. And can you believe nowadays they can even print on a computer? And this is the latest one, which I got it in Denver. And then see what happens. It's called Bose-Einstein condensate. And that one is 400 nanokelvin. You can see it's forming already. And this is 200 nanokelvin. This is 50 nanokelvin. So you can see how they are. See how blurry it is, but gradually it's becoming focused. And this is another one. I had this in like year 2000, I remember. This is for the cesium, and you can see the way it was colored. It was unbelievable how clear they are. I have to, tell something, Overall, the atoms in average is a nanometer. So imagine this is 7 nanometer, and this must be almost 1 nanometer. Okay. I don't know why I have seen so many experiments in MIT, so many places like, YouTube, there were some, universities, and in fact, nobody mentioned kinetic energy. And then I had to mention this because it's extremely important. Let me remove this so we'll have more space. Because what happened, liquid nitrogen is extremely cold, and what happened, we are reducing kinetic energy as much as we can. This was great scientist. The reason why I have this, because this has to do with the kinetic energy. Before Mr. Brown, people had no idea how the atom was. This was way before the Boltzmann and James Clerk Maxwell came up with the kinetic energy, and in fact, gradually, the atomic structure was getting born. And after so many years, Niels Bohr came over in 1930, and he was genius also. He came up with, atomic structure, and before him was Ernest Rutherford. But this man I mean, he was from England, botanist, and he changed the world. What he did, one day he had some pollen, he put it on the microscope, and then he realized, oh, it's a different world. This was, let's say this number 8 is a pollen, number 4 is another pollen. They were going zigzag, zigzag, and there was so much motion, so he became up with this Brownian motion. And in fact, Albert Einstein had two best buddies. He was one of them, and Michael Faraday was. And he wrote so many articles for Brownian motion because Albert Einstein knew that this is going to change the world. Because what he did under microscope, he realized what we see with the naked eye is nothing. You have to put it in a microscope and see. If you remember in my last theory, the theory of separation of charges said, scanning, tunneling, microscope changed the world. We can see so many things that, we had no idea how this was. And in fact, this is the story for Mr. Brown, and it's called Brownian motion. Let me see, his name was Robert Brown. And he was doing this with microscope. He realized that they have a lot of kinetic energy, and this changed the world. So I'm hoping that most scientists, when we're talking about superconductivity, at least they have to mention few minutes for the kinetic energy. But to be honest with you, nobody did. Okay. But I did something extraordinary here, which I've never seen anyone did this in like a superconductivity, because see, we have conductor like metal, like I'm talking about like silver, copper, gold, and they can conduct, and especially copper has a lot of free electrons, and best is the silver, but it's expensive, that's why we use copper. And then I had to correlate that, Teflon, which is non-conductive, and it does so many things. I will show you, and it will blow your mind, because what experiment I'm going to show you, no one has ever done in the history of science. So at the same time, there was a scientist. His name was Fritz London. He came up with different ideas. He was another German genius, and it's called London dispersion forces. Let me put this up, and then I will tell you why do I have to explain these London forces, because they're all related. If you remember a few minutes ago, I talked about Leon Cooper, and he was also a genius. He was a fantastic physicist, and what he did was like breakthrough in science. He realized that that when the energy is so low, the electrons practically should expel each other, or another is going to be repel each other, but no, they don't repel. They join together, and then they help to conduct electricity in superconductivity. Sometimes I think about four forces in nature, and we realize that protons, they never repel each other. They do. But what happened? We're talking about nanometer. So did Leon Cooper did. Leon Cooper was talking about nanometers. Few nanometers, it means you put few atoms in a row. So in that short thing, electrons can join together and conduct electricity. So what Mr. London did, he said my best idea was Teflon. The reason why Teflon has amazing properties. Not only it changed our world, and it was artificial, and it was accident when this was discovered in New Jersey, but it changed everything. And then I had so many years, it's been like year 2000 I started with Teflon, and then I realized one day it came to my mind that, Vahan, if you can accelerate the charges in Teflon, you will be able to get alternating current. First of all, I said, no, that's not a good idea. It's not going to work, but it worked. So Mr. London, what he did, he said, if we have like a Teflon or plastic or anything like this, you can see it says this is what it said: temporary attractive force due to the formation of temporary dipoles. If you remember, I talked about dipoles in the theory of separation of charges. Is the smallest thing, and it is amazing how small it is. And a scanning tunneling microscope shows in 1 millimeter copper wire, there are 1 billion dipoles. Well, dipole means you have like positive and negative charges equally, and they are extremely small. And what he said, this can assume, polarity and conduct electricity. You can see here, they are symmetrical, but here you can see they are off-center. So what happened, see, positive here, but electrons are here. So they can conduct electricity. This is Teflon, and then everyone knows what Teflon is, and it's called PTFE, and this was by accident invented. His name was Roy Plunkett in New Jersey in 1938. Due to London dispersion forces and high electronegativity of fluorine-4 and highest in elements, fluorocarbon, solid, high corrosion resistance, very non-reactive. I have to give you a history for fluorine, because fluorine, if you go back in atomic structure and check everything else, you can see that fluorine is the most reactive element in the history of mankind. They know that fluorine is so, and in fact it took so many years they could not separate the fluorine like the other ones, electrolysis and things like that. It took them so many years, and finally one scientist with genius, separated fluorine. The reason why is a fluorocarbon. So, I did so many experiments with Teflon. I realized Teflon even attracts Teflon. It depends on how you apply those things. Teflon attracts everything, organic material, non-organic, everything. Even, attracts like a magnet. Can you believe that? So this is a story of Teflon. And I have to correlate my Teflon having like producing alternating current, which some people might not even believe this. I created the alternating current is exactly like the way you do it with transformer and the others, with your Teflon. So electromagnetic waves are amazing. They go in space, and then electric field is becoming magnetic field is becoming electric field, and that's why they just convert back and forth, and then they go in space endlessly. So in other words, there is no way that you can stop the electromagnetic wave. Well, of course, there's no doubt from, here to moon and beyond moon, Mars, it just loses its energy a little bit. And this is the sketch of electromagnetic wave. So the reason why I'm doing this, because I want you to know that, I had to correlate the Teflon to, conductive things. And in fact, my main idea was to explain this tank circuit, because Michael Faraday was so genius. He invented the capacitor, and if you one day have a chance, if you just split a capacitor, you can see it's just like a shiny things inside. It's not conductive anything, but what happened, it is storing charges. So this was amazing in electronics. I remember this was my main object when I was in college. I remember, see, capacitor can discharge, and inductor, which is inductive, which is like a coil, can be charged, and then this can be discharged, and then charge the capacitor back and forth and back and forth. And imagine if you have a transistor here, you can have the perpetual motion. Well, of course, always, laws of thermodynamics says everything, even in atomic or non-atomic or subatomic level, they lose energy. That's why the second law of thermodynamics says nothing is perpetual. Always you need to bring energy. In other words, if you want to sustain the oscillation in anything, and that's the reason why I brought this in my equation. I just wanted to know that you guys know that Teflon is so important, even though it's not conductive, but we can use it to have alternating current. But before I start the Teflon, I have to show you something so important. When I started the superconductivity, this was year 2000, and I remember I had so many physicist friends, and then we came up with this idea, which is amazing. You can see this Teflon, this is from a microwave oven. It's extremely powerful. I call it donut shape. But you can see inside, it is non-conductive. So I had to buy this from, a special place. This is a plastic ball bearing. So in other words, I have no, connection. And this is also aluminum, and this is a wood. So the only thing can do here, see? And in fact, I remember his name was Samuel Earnshaw. Long time ago, this scientist says there is no way you guys can do like suspend any magnet. But he was wrong. See, this is the only way. If you have something like this, you can suspend. But I came up with something else. I realized that superconductivity is suspended in air, but what happened to the gravity? And my guess was right. This was year 2000. And then I brought up with so many physicists in CO Boulder. They said, you know what? We have no idea what happened to gravity. I said, no, yeah. Neodymium is going above the superconductor, but it has to be cooled, and it's just suspended in air. But what happened? If that neodymium is like 25 grams, it's added. So this experiment shows that, I was right. Why I was right? Imagine this base is 147 grams. This magnet is not suspended. This one is 188 grams, and the top one is 187 grams. But I will show you what I discovered, which was breakthrough in science. You see? This takes probably 15 seconds. Did you see that? 15 seconds. But if I put this on, see? Weightless. This rotates 3 minutes. Can you believe that? The reason why the flux lines are helping, is like a springs. So of course I'm not going to do that. And then I had to do also electromagnet. I realized it's the same thing. But how could I prove my point? So I put everything on a scale. Let me turn this on, you can tell me. So when I put it on a scale, I'm hoping you can see my scale. So it shows 1,132 grams. When I add this up, even though it's suspended in air, but it's adding up. See, now I got 1,852 grams. See, the scale shows. And then I realized I can also do with the electromagnet. This electromagnet or coil is exactly 51 grams. If I put this on a 12 volt And then what will happen, instead of 1,852 grams, get 1,930 grams. So I have to do like a S to S, so it will be repelled like this. Let me show you. This is a 12-volt battery. Let me see which one is the positive. This is positive and that's the negative. This is the negative. And this is positive. See, if I put this on 12 volt, it's going to repel. Did you see what happened? Let me show you. See? When it repelled like this, it doesn't matter, but still that 50 gram is added. So this was amazing experiment, and then I realized that, even on new theories, they say that, the gravity adds up. It's absolutely right. The gravity adds up. And this experiment shows, well, of course, there was another one that I have to show you. No one has done this in history. And this is so important. I have to get a piece of tape here, and then I will show you. Okay. If you remember, I said this is levitated, so that can go to 3 minutes and so on. But laws of physics tells me if I can extend this from the both sides or from all around, so I can have like 10, 11, even 12 minutes. So what I did, I came up with this idea. I give him more. See, still you can see it's levitated like almost 1.5 centimeter. Can you believe when I rotate this, it rotates 7 minutes? The reason why is suspended. And in fact, I have to work on this, and then because I'm going to invent new way how to harness the windmills and things like that. And I'm hoping by next experiment you can hear that I invented something amazing for the windmill, and then I'm hoping I can do that because of course we have some magnets. I can buy huge magnets. They can levitate almost 10 kilograms. Well, these are not powerful. They can levitate maximum like 1 kilogram or 2 kilograms. Okay, so this is the one. Now about the superconductivity, I have so many experiments I show you guys. So what it is, superconductivity, let me turn this on. So this is the minus, this is the plus, and this is the minus. Let me show you this. So if you have like a neodymium magnet, what happened? It is using its own flux line. By the way, flux means, it's a Latin word, means to flow. Flux lines are continuously going, from north to south and north to south, and they never stop and they never start. It's always continuous. And I just wanted to demonstrate, how that works. So I came up with this experiment. You can see I have like different coils, and these are 12 volt DC. And then when I have neodymium, so I compare this to the superconductivity, and this is like my superconductor, and this is my neodymium, and then you can see when I energize this, you can see this is going in a loop, non-stop. Let me see. Did you see that? It goes non-stop. Well, of course, I have more. I have to get those in the room. Okay. See, these are almost as strong, ceramic magnets, and then you can tell this is exactly what happened in superconductivity. No, that's not right. What happened? See, it's going round. See what happened? That's exactly what happened in superconductivity. See? If I hold this for hours and hours, it's going to go round. The reason why is repulsion. So this neodymium magnet is using its own flux line. It's going round and round and round. But there's a problem. As long as it's chilled to the superconductivity state, and then it can go. If it's getting hot, it's going to stop. Well, of course, I have more. This is another one. This is another one I'll show you. Superconductivity is amazing. When you have a magnet like this, these are different magnets, cylindrical they call it. So it doesn't matter how you put it, it's 360 degrees repulsion. And then 360, it doesn't matter if I rotate this 360 degrees, it's always repulsion, always repulsion. And if I do it the other way, it's going to be attraction. And that's what happened in superconductivity. No matter what, is always repulsion. See, let me show you here. Oh no, it's the other way around. See what happened? It's going to go forever because it's the repulsion all around. Okay. And this is the famous experiment I was going to tell you guys with Teflon. This is extremely powerful. I had to put some rubber so it won't shake that much. And in fact, the motor has 20,000 RPM. But unfortunately, I don't have that, lithium-ion battery can go to 20,000 RPM, and then I can get like almost 8 or 9 volts AC. But I have this regular one, which is 12 volts. It goes maximum 10,000 RPM, I will show you. And it's amazing how it works. And I'm correlating this to the superconductivity that, they don't have to be superconductor to conduct electricity, even Teflon. But the amazing thing about the Teflon, I have to explain. Teflon can attract everything. If you remember a few minutes ago, I talked about fluorine, and that, because it's a hydrofluorine, and fluorine has the highest electronegativity, which is 4. So when this Teflon is going like this, I will show you. See, I have some transducers here. Like this transducer can measure voltage alternating current from 12 volts AC to 1000 volt. So is this one, so is this one. They're good transducers. But all they do, they just flicker a little bit, you know, they show the light and then the sound sometimes. Let me see if I can do it over here for you guys. Well, of course, I have to turn it on. This is the plus. This is the plus. If I hold these transducers even 1 meter above, it's going to show that, you know, the alternating current is here. Let me show you. Did you see the light? It's extremely powerful. I have to explain this. This is a small Teflon and it can go to 10,000 RPM. I have a thicker one, but of course this is not good enough for that because, like I said, I need a lithium ion. I was not happy with these transducers. I said I have to do something better, more scientific. So I have a good equipment. They're all from Holland. These are good, fantastic, clamp meter. When I hold the clamp meter here, put it on alternating current, set on alternating current, it's showing a voltage here. So what it is, I can't have voltage when it's like this. There is no way I can have voltage over here. Or when it's accelerated here, 10,000, I calculated exactly 1 second goes to 170 times. In 1 second, it rotates 170 times. And imagine those charges are accelerated. Okay, let me see if I can hold this and then I can start this. Yeah. Well, of course, I have to work with 2 meters. This is not clamp meter, this is the regular one. So I put this one on AC also. So let me start this. I have to get this meter toward the camera so you guys can see. I'm producing exactly 3 volts AC, and even if I do it with 1 wire, I can have 1.4 volts or 1.5 volts. Let me show you. Did you see what happened? Even with 1 wire, I can get 1.4 volt. And then I have to try something else. I came up with my own transformer. Let me show you. I invented my own transformer. Let me show you. We put this down. This is so heavy and it makes a lot of noise. Okay. Let me put this down. I came up with my own transformer. It's just so simple, but I invented this. See, normal transformers are like this. You have seen it so many times. I would say 99% type 2 transformers. We got the primary and then the secondary, and then of course this is not the core, but we have like core like this which goes all around it, and without the core it's not going to work anyway. So always we have primary, secondary. But they came up with a better idea which is more effective. So this is my invention. So you can see it's only one winding. No, it's not. There's underneath. So underneath is the primary, and this is the secondary. So what happened, the induction is 100%. And then you can see all around it, I have those. Let me show you. So if I plug this in, I calculated I didn't want to have real powerful, so I get like a maximum, I get let me see, 16 volt alternating current. Let me see where that light bulb is. I'll show you guys. Oh yeah, here. There's a light bulb here. So when I connect my transformer, you can hear that noise, big noise. Did you see that? Light up the lamp. But there's something important here. This does exactly like the Teflon did. If I connect this to my meter, fluke meter, even one wire shows voltage. Let me see if I can show it over here. See, I'm going to do, it doesn't matter which wire. Did you see what happened? It shows the voltage here. It doesn't matter which one I do, it shows the voltage. But if I do both of them, and it shows the actual 16 volts. See? Okay. In fact, I got some superconductor, but of course they are not real good ones, they're small ones, and then I realized they conduct electricity with my meter 100%. This is exactly like, and I have never seen this in any book or any places. Like, this is so important, I want you to pay attention, see what happened. This is conductor like copper or anything, silver or what. And this is the superconductor. See, it goes around that. So in other words, it's expelling. And this is diamagnetic. And this is paramagnetic. Well, of course, I have to explain, this superconductivity is called type 2. And then they have a little bit impurities in that superconductor. Flux line can go a little bit on those. So in other words, the way it is not conducting 100% the flux line, it's conducting a little bit. And I have to explain about the permeability, which is so important. It shows that how good an object or material can conduct magnetic lines or magnetic flux line. That's called permeability. And iron is the best, that has the highest energy per nucleon. That's so important in our life. Iron does it. And this is the conductor, superconductor, diamagnetic, and paramagnetic. And then I realized flux lines can penetrate everything. Glass, like, silicon. How did I do this? I had to use Gauss meter. See? If I turn this on, I can show you. This Gauss meter is so important in my life. It shows everything, whatever I needed. See, this is a neodymium. That is the most important magnets or powerful. You see what happened? It's got 3,400 Gauss. So how did I do this? I put this underneath and then I measured over this. Then I realized it's almost like 145 Gauss is going through. These are exactly 1 inch or 2.5 centimeters. So is this glass, is 2.5 centimeters. See, it's showing like 134 Gauss. So my idea was that, there is no shield for magnetic flux lines. This is a lead, and this is exactly 2.5 centimeter. And see, it's 165 Gauss is going through, even though it's so thick like this. See, I have another one. I have copper here. This is also 2.5. I put this underneath. So this is a neodymium. I put it underneath. This shows 110 Gauss going through it. And then I have Teflon here. Let's see. I put it underneath. Teflon like this. This shows 72 only. It's less conductive. And then I have ceramic here. It shows 254 Gauss. And then I have rubber here. It's showing 234 Gauss. So in other words, it conducts. Flux line can go through everything. But unfortunately, I didn't have the liquid nitrogen, so I came up with so many ideas that unfortunately I don't have the tools to do it. I need to ask a university to let me do those. And this was like a breakthrough in science. Let me show you. Like I said, I could not finish this. Always I postponed this, so almost 20 years, and finally I decided to do that. If a university let me do this, this is going to shed light to so many things in superconductivity. And imagine you have your liquid nitrogen, and you have your superconductor, and then you have your neodymium. I came up with this idea. I make a hole. Let me see where that is. Yeah, it's here. Imagine the new superconductors are almost this big, like I would say, like 4 inches across. And then if you put this probe inside the superconductivity while chilled, and then this probe shows exactly if the flux lines are going through it or not. Well, of course, I have to explain it goes through a little bit, the reason why they have impurities. In those days, I was in college, they would call it doping. The reason why, if that transistor or silicon has no doping, it's not going to work. They have to add a little bit impurities or doping so the silicon can become conductor. So they made transistor, diodes, and so many components. So if they do this experiment, I know they have like a problem with insurance, but I will instruct them how to do it. If they do this, that is going to be a breakthrough in science. So they put a hole in a superconductor and then put this probe inside. Then when it's cooled, it can show how much light, flux lines is going through. And my second thing was, instead of using neodymium, I can use coil. That was another groundbreaking idea. And the coil, the reason why I use coil, because I can increase and decrease the voltage, and I can see if the levitation is changing. And imagine these two concepts can make a big difference, so the scientists will understand that, they don't have to use the neodymium all the time. They can use the small coils. And then, in fact, I made some, which was amazing. The little coil like this, I had 1,200 Gauss. So they can suspend this in air and then increase and decrease the voltage, and that will shed light to so many things. Sometimes, I wonder why it's so important that, you have to let the student, well, of course, I'm not a student, but I'm acting like a student, because sometimes some professor thinks that, if you're a science experimentalist, you don't know anything about science. No. If they let me do this experiment, I can solve so many problems in superconductivity, which these things is never been discussed, that, you make a hole in a superconductor and you put your, DC gas meter in it, or, you change this with the electromagnet. This has never been discussed, and I'm hoping if any university decides, I've been happy to pay for all the expenses myself, go there and even get some equipment there, and then work with them. And like I said, I'm not going to do anything. I'll let them do the experiment, and then I will just instruction, give them some instruction how to do it, and I'm hoping that, this will help, solve so many problems. And I have, I think, one more here. I have to display this. This is another poster, I forgot. Okay. See, it says Newton cannon, levitron, a spinning top, International Space Station have one thing in common: defying gravity with velocity. That's absolutely true. Think about a space station, International Space Station. It's going like 90 minutes. And this exactly, many years ago, I remember I compared this with Kepler, and in CU Boulder, they loved it. They said, "Wow, where did you get your PhD?" I said, "I don't have a PhD in physics. I'm a physics experimentalist. Like Albert Einstein, I learned myself. My major is electronic, but it's been 30 years I'm doing physics. And you know what? Barnes & Noble was my home. I was there every day studying books and then doing experiments as much as I could. And imagine this is going 90 minutes. This one is spinning, and as long as this is spinning, it's not going to fall. And this was so important, this experiment. Sir Isaac Newton never did this. This was a thought experiment. And anytime I watch soccer or football or any international event, I said, "Thank you, Mr. Isaac Newton." Say, it goes around all the satellite and things like that. It's based on this. And imagine how genius Sir Isaac Newton was. 300 years ago, he said, if you have less, it's going to fall. More, and this goes around. And this is exactly what happened with the satellite. So I'm hoping, I did not cover everything, unfortunately, because like I said, I don't have the tools. I was going to buy liquid nitrogen, but unfortunately I couldn't find superconductor like this, because my superconductor was so small, so I couldn't continue this. But like I said, if they let me do their lab, I'd be happy to shed lights on so many things. And if you liked my video, I was wondering if you can go ahead and subscribe it. And anytime you have any question, you can email me, vahandavudyan@aol.com. And my next one is going to be how to visualize Michael's Faraday lines of forces. And then I forgot to mention something like that, because I mentioned the flux lines. And I have never heard or seen in any book or anything that said those flux lines are repelling each other. Can you believe that? If you have like iron filings, you can see there's a line here, there's a line next to it, parallel lines, and then I realized those lines are repelling each other. And then in my next experiment, which is how to visualize Michael Faraday's lines of forces, I will explain more in detail. And thanks a lot for watching. And I know my lab is not equipped with everything, so I couldn't handle everything. I apologize for that. But like I said, as much as I could, this was my ideas that, you can correlate the non-metal with metals, and then superconductivity, and how important in our life is superconductivity. But if in one day it becomes true, we don't have to pay for electricity. But unfortunately, it is not going to come true, because whenever you have laws of thermodynamics, you have to pay for it. It's not going to change anything. Thanks a lot for watching, and I hope to see you guys next time. And like I said, anytime you have any concern or any questions, I'll be happy to help you. Even if I don't know, I will dig it out for you, because I'm a good researcher. And thanks a lot for watching.